All right. It is time, so I'm starting the recorder. And today we're trying something different. I'm using the wireless mic. So what I'm doing right now is I'm trying to make sure that I do not saturate the channel by kind of tweaking the gain of the sound card a little bit. So when you guys play it, you can tell me, whether it's too soft or whether it's too loud. But it looks like, I'm doing it just right because, it's not saturating the audio channel. Alrighty. So the good thing is, no matter where I walk in the classroom, it will still pick it up the same way. The bad thing is it won't pick up what you guys are asking, so I will have to repeat your question, so it'll be recorded, for those questions. All right. So now that we have this out of the way, let's talk about your homework assignment, okay? Yeah. Okay, so first of all, we want to know how to get started with a homework assignment, which is downloading a file, get it onto the virtual machine, and untar that. Are there any questions about the setting up of the folder, the untarring part? Okay, no questions about that? Okay, I don't think I saved mine, anywhere that I can reuse it. So what I'll do is I'll re-download it and do it again. So this is the tar file, and you don't even bother to open it, especially in Windows, because Windows would not know what to do with it. In Linux, on the other hand, you do have a few options. I will do this in the temp folder, so once again, it's not going to be saved. And I don't know where it is saved, so I'm going to try out here. Nope, it's probably my downloads folder. Downloads, and it's called hunt.tar.gz. There you go. All right, so this is the command that you run in order to unzip the file. There's only one file inside, which is called bunny.s. Okay, so we go to the folder. We take a look at bunny.s. And this is the program. This is the code. You can only change the underscores to something. Okay, you can specify expressions in place of the underscores, but you cannot change the addressing modes. So that means you can change whatever this is supposed to be, whatever this is supposed to be, and whatever this is supposed to be. So there are three places where you can specify something, but you cannot change. You cannot add new instructions. You cannot delete instructions. You cannot change the addressing modes either. So whatever is an immediate operand has to remain as an immediate operand. Whatever is a direct operand has to remain as a direct operand. All right? So are there any questions at this point? Okay, no questions. Any additional questions about the homework assignment? Yep. Okay, let's try to figure that out. Okay, so let's see how we can figure out, whether .long is 4 bytes or not, using various means. Okay, the first thing we'll do is, okay, this is, I know, you probably think, well, it should be told, whether .long is 4 bytes or not. But if you're not told, what are you going to do? Well, you can look it up. Okay, so you can look up the assembler reference manual. You can also just Google and look it up. So just Google. Well, I'm already using Google here, so we'll just look up .long in the GNU assembly, in assembly code. All right. And you don't want to use a Stack Overflow because that's usually just well, this is interesting. This is from UC Davis, by the way, and this guy is teaching assembly language programming pretty much the same way that I'm teaching it right now. This is probably useful. Okay, so we want to check out this one. But before we go this far, the other thing that we can also do is to check out the reference, documentation that we have in this class. And failing that, we'll still be able to find out. Okay, so I'm just going to go through all the different options to find out what is a .long. All right, so the first thing we want to do is to go to the reference manual, if there is one here. Reference manual of the assembler. So I'm going to open it as a new tab so we don't lose track of the original one. All right, so now we have this The first thing I would do, since I'm really lazy, is to use the search feature in a browser and just look for .long right here and click it. It says it's the same thing as .int, c.int. So, and it even includes a hyperlink, so we go to .int, it's the same thing. So what if this is missing? What if I don't have access to this documentation? Can I find this out experimentally? That's the question. How would you find it out experimentally what is a .long? There are several ways, okay, so I'll show you a few, at least two. Okay, so the first one is you just go ahead and write a very simple program. It doesn't have to be long, doesn't have to be big. It's just, has to be relatively simple. So we'll say vim, I don't know, how long is long, okay? And what we'll do is we'll just do one thing. You'll go to the .text section here, and then we have L1 .long. Give it a particular pattern, so it's not something that it's not just 0 because zeros are everywhere. So we'll give it a particular pattern. Doesn't have to be long either. Okay, like 7 is fine. And then we immediately define another label. Okay, and this is already enough for me to tell what is a .long, and I'll show you guys why it is already sufficient for that purpose. But in order for the linker and stuff like that to work, we have to have an _start. .global _start, like that. Okay, so this is just to make the linker happy so that it would link the program, because I never really intend to run the program anyway. Okay, so save everything. ASG stabs -o .o and .s LD -o how long is long, how long is long .o, GDB how long is long. Okay. And we'll list the program, put a breakpoint on the one instruction that we actually do specify, which is on line 5. Run the program, and now we have stopped. So what I want to do is to find out what is L1 and what is L2, okay? Because the labels L1 and the label L2, the address, okay, the difference between those two addresses is going to tell me what? The length, the width, or the basically the number of bytes used by .long. Okay, so we'll go ahead and do that. Okay, so we can say print &L1. Remember, we have to use ampersand because GDB makes an assumption that labels are variables, which they are not. Okay? So we find out the first one is ending at an address of 54. So we want to look at the second one, which is L2, and L2 is 58. And you can even, do a subtraction. Okay, you can actually have printf to do the actual subtraction for you to find out, how many bytes are in between. But it's fairly obvious. Okay, 58 minus 54 is exactly 4 bytes. Okay. But how do we know how those bytes are arranged? Well, you can use the x command to do that. So you say x/1. Well, if you don't know how many bytes, go ahead and list, like 20. Okay. And you can say 20bx, okay? Each one is a byte, and we want to print it in hexadecimal, starting at L1. So now you have, these bytes here. So you can kind of tell that these 4 bytes belong to L1, okay? Because we know that this is, this is _start. So we know 7 is represented by 32 bits in this particular manner, which is little endian, because 7 is the least significant byte, and then the most significant bytes are all zeros. So that's one way to find out, what is a .long. Are there any questions about this part? No questions? All right. Any additional questions? Yep, go ahead. We know 90 is _start because that's what it says here. And this is location 58. Yeah, because this is location 54, that makes it this 55, 56, 57. So this byte is location 58, which also so happens to be called _start. And we can also confirm that _start is the same as exactly, L2, because we can just print it out as well. Okay, very good. Any other questions about the homework assignment? No questions? Well, we'll go take a look at the homework assignment one more time, and then if you guys have any questions, go ahead and ask. Oh, no, that one. There we go. So this is your homework assignment. If you have any questions about the assignment itself, go ahead and ask. Yep.
And how is BX and BH different?
Well, you have to, I think it's in one of the notes. So let me see if I can find it. Okay, so you want to find out, how the registers are organized. So we'll go ahead and find the addressing modes and memory allocation. And we'll check out this one. It doesn't say it. Okay, so we have registers here. There you go. All right, so you want to find out what is AX versus BHBL. Okay, there are 8 32-bit registers. The first 4 general-purpose registers are extensions of AX to DX. EAX is the enhanced one. Let's see. There we go. So the i386 has some interesting combinations of registers. Let's start with the 8-bit registers. The 8-bit registers are ALB, AHBL, BH, and so on. The L stands for low, the H stands for high. There are 4 general-purpose 16-bit registers. Each one is a concatenation of the matching 8-bit registers. All right, so let's just read this sentence and see if we can decipher what this means. Well, first of all, did you guys read this part? Yes? No? I don't even know it's there. Okay, if you have not read it, it's probably best if you try to read it and understand this part, because otherwise, if I just tell you, it's not gonna, you're not gonna remember as well. I think there was one class I used a spreadsheet to illustrate it, so that's also something that you can refer back to. Did I explain it using a spreadsheet? Yep. Okay, so there you go. All right. So basically, okay, in general, okay, this is just a general statement. BH, okay, the 8-bit registers and the 16-bit registers are nothing more than windows into the 32-bit registers. So as far as this class is concerned, okay, the 32-bit registers are the quote-unquote full registers. They are basically the entire thing. But of the entire thing, like EAX, which is a 32-bit register, you can look at the least significant 16 bits as AX. But of the 16 bits, that is AX, you can also break it up into AL, which is the least significant A bits, as opposed to AH, which is the second least significant A bit of EAX. So those are the windows, okay? How do I know how this stuff all works? Okay, let's say you have some basic understanding of how EAX relates to AX, relate to AL and AH. What do you do next? You write a small program to test it. Exactly. What kind of small program are we talking about? Something that is really small, something that's easy to figure out whether it's working the way it's supposed to or not. Okay, so we can say test.s. Okay, and I'm just going to show you some of these instructions here, so we can move along. 0x specify all 32 bits. Okay, so you can specify something like ABCD 0, 1, 2, 3. Okay. As a bit pattern, put it into EAX. And then the next instruction, I'm just going to put something that is not, ABCD 0, 1, 2, 3. So 7, 8 is a good byte, okay, in hexadecimal. And I'll stick it into, let's say, AH, okay? And then you want to find out, how is EAX changed by the second instruction. That will give you an idea of what is AH. All right? Are there any questions? The best part of a programming class or a computer science class is you can try this stuff out and it's not going to hurt anything. Okay? This is not a class about disarming bombs, okay, where you may not want to try, oh, I think it's the red wire, let's try that. Okay? That usually does not work if you're trying to disarm a bomb. But because it's a software class, it's a programming class, this is the best way to learn things. Okay? Because you get to observe it, you get to know the tools better, and as a result, after you do something like this, once you understand it, it will stick. Okay? Because you're not just memorizing something that I wrote. All right? Any other questions about the homework assignment? Which is this one here. Has anyone tried to assemble this program the way it is? Okay? Of course it's not going to work because the underscores are not defined, right? Okay? So let's give it a try and see what happens. Okay? AS G steps -o bunny dot s, and the assembler actually works because it is seeing underscore 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 as a label that is yet to be defined. And that's why the linker is the one who's going to complain and say, hey, what is underscore underscore underscore? It's not defined. And that's why this is the part where it is going to complain because it says, hey, that's a label that nobody has defined. So what you need to do is to focus on one thing at a time, okay, and debug the program like one step at a time. But knowing how BHBL, BX, and EBX, how they relate, is really the first step. Because otherwise, there's no way someone can start working on this homework assignment. So working on this homework assignment is studying. This is how we study. This is how I would study for this class. Okay. Any other questions? No questions? Yep. Go ahead.
So the 0, 1, 2, 0, 3, 4, 3, 2, 3 are just labels, they're not.
What? Sorry. Say again. Let me turn on the line number so you can tell me what line number we are talking about. On lines 2 and 3, 1, 2 is a number, is a value, it is 12. Okay, 0x12 is a number, it is hexadecimal 12, and then 012 is octal 12. So those are all values, but specified in different bases: base 10, base 16, and base 8. So when you can see these are different numbers, but they're specified in different bases, then you have to kind of do all the base conversion stuff because I want EBX to end up with that base 10 value. Now, how do I know 3858 80604 on line 14 is not base 16? It is not octal. It has no prefix. Exactly. It has no prefix. This is the same way in C and C++ and Java and most other programming languages. Use the same convention to indicate whether it's a base 10 number with no prefix whatsoever. If it has a prefix of 0 all by itself, it's octal, base 8. If it has 0x as a prefix, it is a hexadecimal or base 16 number. And that convention goes a long way. Okay, if you want to program in any programming language that's based on C and C++, and I would suspect that includes Python, it would include PHP, Perl, and so on. They all follow the same convention. Okay, so your job, part of your job is to do base conversion as well because you're looking for a particular bit pattern. Looking at a base 10 number does not tell you what the bit pattern is, so you have to do the base conversion as well. Do you need a calculator to do the base conversion? No, because you got GDB. GDB is the answer to everything, as you might have noticed. It's kind of like a tricorder in Star Trek or the sonic screwdriver of Doctor Who. Any other questions? No other questions? Any questions about the addressing modes? Okay. Alrighty. So if there are no questions, we are going to move on and talk about the next topics. So this is Egg Hunter, your homework assignment. There will be another, Hunter homework assignment, but I will probably change it a little bit. But right now, we are going to move on to subtraction and comparison, okay? Which is something that we have kind of talked about, but we have not really kind of talked about. Well, actually, this is something that we have completely talked about, because we did talk about all the flags. We talked about the Z flag, the carry flag, the sign flag, which is the most significant bit of the result, the overflow flag, and the L flag, which is kind of invented. It's the exclusive OR of the overflow and the sign flag. So that's the stuff that we have talked about so far already. The next question is, but how do we apply that in programming? Okay, so let's think about it a little bit for the time being. Well, let's see. Should we talk about the add instruction first? The add instruction is not here because I put it into the earlier part of this class. So let me go find that first. The add instruction is not really that much fun because it's mostly stuff that we already know. And I would think it belongs to here because we talked about the add instruction here. Binary numbers, subtraction, addition. So let's take a look here. Here's the link. Nope, it doesn't talk about the add instruction. I have to find the discussion of the instruction itself. That probably is it. That's it. Okay, there we go. Let's check this out. Okay, addition, subtraction, the use of status flags. That's binary addition. I'm looking for the instruction itself. I cannot remember where I put it, so I have to track it, somehow. But before we do that, because that might take some time, I'll just go ahead and illustrate it using examples. Okay, the add instruction is very much like the move instruction, except it doesn't copy the first operand to the second operand. It adds the first operand to the second operand. That's the only difference. So let's go ahead and take a look at a very simple program to do just one single addition. So we'll go ahead and take a look at this particular program. And I will make this program so they can actually run. So this way we can actually test it and see how it works. The first thing is we move a particular number or a certain value into, say, EAX. So we'll say we put, I don't know, let's say, we can use decimal numbers if we want to. So 1,000, put it into EAX. And then the second instruction is add L. We can specify, well, let's try this. Let's see what it does, okay? Because I claim that the add instruction is adding the first operand to the second operand, okay? Which means, in general, this is how it works. So if you have an add instruction, you have the first operand, operand 1, and you have the second operand, which is operand 2. The result of the add instruction is the same thing as, if I want to put this into C++ notation, it's the same thing as operand 2 plus equal operand 1. Okay, does everybody understand that notation? It's called a compound assignment operator in C++, in C and C++. So basically, it is the same thing as operand 2 equals to operand 2 plus operand 1. Are there any questions about the general format of the add instruction? So given that is what the add instruction does, which is adding the first operand and to the second operand, which means the second operand also stores the result of the addition. What do you think is the result of these two instructions? What is EAX going to be after the second instruction? 2,000, exactly. Okay, so we'll go ahead and give it a try. Okay, because now we have a suspicion of this is how the instruction works. So we'll go ahead and give it a try. This is the exit code. So we have the. We are not going to use it, but I will still put it here. But this is not really useful because addition is commutative. Yep.
Last time, just how you used NOP, is that the same thing as this exit command?
No, NOP is just no op. It does not do anything. So if you just use a no op instruction, your program does not exit normally. It will most likely quote unquote crash. This will exit normally. Yep. All right. So let's make this a little bit different. So instead of this, we'll specify $512. Okay. So what do you think this time EAX should end up as? 1,512. Okay, because we are adding 512 as a constant to EAX. Is that okay so far? Okay. What if I make a typing mistake and forgot the entire $ in front of 512? What do you think this program is going to do? It will crash because it's trying to access which location? Yep, location 512 is not a place where your program has access to. Very good. Okay, excellent. Okay. What if I do something like that? What is the end result after line 8 executes? What would be the value of EAX? 4,000 is correct, not 3,000, because we are doubling on line 7, so that turns EAX into 2,000, and then we double again on line 8, so 2,000 times 2 is 4,000. Very good. Okay, so I think we get a general idea of how the add instruction works. Okay. Yes, kind of. All right. So let me change this program to something that's a little bit trickier. So we'll put this. I have to hand select what I want to do here. So 1023. Okay, this is a very exact value, and then what I'll do is I'll change this to add byte, and then change this constant, and say let's just add 1, but this time we're adding 1 to AL. That's it. Okay. So I want to ask you basically 2 questions. The first question is after line 7, what is the value of EAX? And then the second question is after line 7, what is the value of AL? Okay, that's the question. So how do we figure this out? Well, we just assemble the program, run it, and figure it out in GDB. Well, GDB is useful for verification, but it's not useful as far as understanding this is concerned. So what we want to do is to figure out, okay, do we understand what the first instruction is going to do? Yeah, we kind of know that, right? So EAX is going to get the value of 1023, and 1023 in base 2 is what? 1024 is 2 to the power of 10, so that makes 1023 what kind of a bit pattern? 10 ones. Okay, it has 10 ones. Well, if EAX has the least significant bits being 10 ones, okay, what do you think is the value of AL, which is the least significant 8 bits of EAX? It'd be all ones, okay? How many ones are we talking about? What is the width of AL? It's 1 byte, which is 8 bits, right? So we have 8 ones. Now, when you look at the instruction on line 7, what does it say? Add byte, okay? Which means the entire width of the operation is 8-bit wide. What happens when you add 1 to 11111111? You get 0. Very good. Okay? The carry flag is going to be set afterwards, but nonetheless, the most important part is it will give you a 0. Where do we store the 0? It's an add instruction. It follows the same rule as what we have just talked about. It stores the result in the first or the second operand? The second operand. And what is the second operand in this case? Is AL. And AL, how does AL relate to EAX? It's the least significant byte of EAX. So now the question is it going to affect the other bits of EAX? What do you think? It's not. Okay, so that means, after the second instruction, after line 7, we will end up with 2 1s, okay, outside of the 8 bits of AL, but then the least significant byte of EAX is going to be all zeros. So when you look at EAX as a whole, it's going to be a 300 in hexadecimal, the 3 being the 1 1 of bit 8 and bit 9, and then all zeros from bit 0 to bit 7. So we'll end up in hexadecimal, it becomes 300, as a base 16 number. Is that making any sense so far? Okay, let's try it. Okay, so now that we have figured out what the program is supposed to do, we can now actually check it out and say, okay, is this what the program is going to do? And by the way, this is related to your homework assignment as well, because now you can kind of get an idea of how the smaller registers relate to the larger registers. Okay, so let's go ahead and do this. gstabs-o add 1.o, add 1.s, link add 1, add 1.o, and gdb add 1. Put a breakpoint on line 6. Okay, run the program. Single step line 6, which is not going to be very exciting because we just get 1023 back. But we can also print it in binary, which is /t, and it shows you 10 ones, which is exactly what it is supposed to be. So nothing really surprising at this point. But there's one more thing I want to do, is I want to look at what is AL. Okay, you can do this too in GDB. You can display the content of not the entire register EAX, but you can designate the smaller register as well. Okay, and it shows you all ones, except this time we only have 8 ones instead of 10 ones. Okay. Then we single step again. This is single stepping line 7. So after line 7, we want to look at EAX as a whole, and it is 1 1 and then followed by 8 zeros, just as what we expected. But then you can also look at AL, and AL is all zeros. Okay, it doesn't print the leading zeros, and that's why it displays just a single 0. But that's basically the same thing as what we saw, what we thought would happen. One thing that I have not done is to print EAX in hexadecimal. So let's go ahead and print it in hexadecimal, which is /x. It is EAX, not just that. There we go. It is 300. All right. So this little illustration is not just for displaying, how to use the add instruction, which is pretty easy, but also to, kind of explain, how the registers relate, which is related to your homework assignment. Any questions about the add instruction? Yep. Because it is 1 1. Okay, so imagine there are 2 leading zeros here, 0 0 1 1. That's 3. And then the 4 zeros being a 0, and then another 4 zeros being 0. All right. Any other questions? No other questions? What is 300 in hexadecimal? If I display in decimal, what is that going to be? Okay, come on, guys, work on this. There are several ways to work on this. Okay, the first one is to understand how a base 16 number works. This is the number of ones. This is the number of 16s. This is the number of 256. So this means we have 3 times 256, which means the product is going to be 768. Yep. And how do we verify that? No need to use a calculator since we have GDB, right? Because all you have to do is to print EAX itself. It is in decimal. It is 768. Why do I ask all of these questions? I mean, you can easily do that on a calculator, but why did I ask these questions? Base conversion for one thing, and also there will be times when it takes less time for you to figure this out by yourself than to pull out a calculator and actually work it out on the calculator. Okay. All right. What about the flags? Okay, the last instruction that we executed was this instruction. We were adding 1 to a bit pattern of 1, 1, 1, 1, 1, 1, 1, 1. Of all the flags that we are interested in, which one is going to be set, which one is going to be cleared? Okay, go ahead. Which one? The carry flag is going to be set. Okay, that's good. And there's one more flag that has to be set as well. Which one is it? No, the sign flag is not going to be set. The sign flag is the most significant bit of the result of the addition. The result of the addition is 0, 0, 0, 0, 0, 0, 0, 0. They're all zeros, which means which flag has to be a 1? The 0 flag has to be a 1. So the carry flag should be a 1. The 0 flag has to be a 1. What about the sign flag, which is the most significant bit? That one is a 0. Okay, it's cleared. There's one more flag that we have to deal with, which is the overflow flag. Okay, do you think the overflow flag should be set or cleared? We add 1 to 1, 1, 1, 1, 1, 1, 1, 1. Does the sign make any sense? The result, the sign of the result, does it make any sense? Okay. Let's think about it. 1, 1, 1, 1, 1, 1, 1, 1. Okay. In sign interpretation, is this a positive or negative number? It's a negative number. That's all we need to know. We don't even need to know how negative. We just know it's negative. We are adding 1 to it, which means we have implicit leading zeros. Is that negative or positive? Okay, that's non-negative, but we'll just call it positive. The end result turns out to be all zeros. Okay, all right. But we don't even care about the value. Is it negative or not? It's not negative. Okay, so we just say it's non-negative. Okay. If it's non-negative, does the sign make any sense? If I add a positive value to a negative value and I end up with a non-negative value, can that happen? Yep. So the sign makes sense. So if the sign makes sense, is the overflow flag set or cleared? It's going to be cleared. Okay. So that means of all the flags that we are interested in, the sign flag is a 0. The 0 flag is going to be a 1. The carry flag is going to be a 1. And the overflow flag is going to be a 0. Okay? So let's check it. Okay? The way we check that is to look at a particular register. It's called the E flags register. Okay? For extended flags. And it has more flags than we really care about, but it also displays just also the flags that we want to know. If you see an absence of a flag, it means it's not set. If you see a flag here, it means it is set. Is that okay? So we can confirm that the carry flag is set. We can confirm the 0 flag is set. But the absence of the overflow flag, which is OF, okay, and the absence of the sign flag, which is SF, means those flags are cleared. All right? The other ones are not really used. IF, I know, is the interrupt flag. And then PF is the partial, or it's kind of like a halfway, carry flag, but we don't really need to use that one either. Yep.
If you have multiple registers, how do you know which one is talking about? If you have multiple registers, how do you know which one E flag is talking about?
The E flags is only going to store the flags of the previous instruction, which means if you have additional add instructions, it would overwrite these flags. In C++, you can write an assembly subroutine to pull that and then call that subroutine from C. Then you can actually pull the E flags out of in C++. Yeah, a part of it has to be done in assembly. But it doesn't really help in C because you have no idea what kind of instruction the compiler is generating. So unless you're talking about the interrupt flag, which does not have anything to do with calculations or comparison, but if you're looking at the flags that we care about in this class, we have no idea whether they mean anything because we don't know the ordering of the instructions. Okay. Any other questions about addition? Okay, addition is really boring. Okay, it's useful, but it's kind of boring. What is more interesting is subtraction. Okay, so let's go to subtraction. Why do you think subtraction is more useful? Because we can use it for comparison. Very good. Okay, so what we want to do is, okay, let's go ahead and do a subtraction. Okay, subtraction 1.s. Okay, so this is just a really kind of simple example of how to use subtraction. So before I use the instruction, I'll just say subtraction is the same way. You have operand 1, the first operand, and then you have operand 2. And the result is basically saying operand 2 minus equal to operand 1. And that really is the same thing as operand 2 is operand 2 minus operand 1. Now, in this case, I have to be more careful because addition is commutative, which means it doesn't really matter are we adding the first one to the second one or the other way around because it is commutative. But with subtraction, it is not commutative. So I have to be very clear that we are subtracting the first operand from the second operand. The result, which is the difference, is stored in the second operand. So lines, let's see. Lines 4 and 5, both represent, how the subtraction instruction works. Are there any questions about the general form of the subtraction instruction? No questions? So we'll go ahead and just do a few examples here. Okay, so we can always move a particular value into a register first, and then we'll do the subtraction, just to test it. So let's see. Okay, well, we'll use byte-wise operation here. So I'll move a 80 into register AL, and I'll subtract byte of 1 from AL. Okay, and that's the entire program. The rest really does not matter, but I still want to put it here just so that we know that this is the exit code. But I will never really get to that point. Okay, there's no need. All right, so when you look at this program, only line 6 and line 7 really do anything that is related to the subtraction. Line 6 doesn't do much. All it does is to move a constant, which is 80 in hexadecimal, into AL. And then the second line, line 7, is going to subtract 1 from whatever AL has at that point. In other words, we are subtracting 1 from 80 in hexadecimal. Is that okay so far? So before we run this program, we want to figure out exactly what is going to happen here. What do you think AL should end up as at this point? 1, say again? 128? Not after the subtraction. Okay, you can call that 127, but what about the bit pattern? In hexadecimal, we should have 7F, right? Because it's the same thing as in binary 0, 1, 1, 1, 1, 1, 1, 1 in base 2. Okay, very good. So that's the first thing we figure out. What about the carry flag or the borrow flag in this case? Should it trigger the borrow flag when we subtract 1 from, okay, that should be a 0, which means it doesn't show when we look at E flags. Okay. What about the 0 flag? That's a pretty clear one. What about the sign flag? What about the overflow flag? Should be a 1. Okay, so let's take a look at the bit patterns again. The first number is 80 in hexadecimal. What does it look like as a binary number? 1 followed by 7 zeros. Okay, so it's 1, 0, 0, 0. That's the 8. And then we have 0, 0, 0, 0, which is the 0. So this is 80 in hexadecimal. What do? We subtract 1 from it, right? Okay. And, if you remember your binary subtraction thing, this is a pretty easy one because, this will keep 0 minus 1 is a 1 with a borrow. But that borrow would also mean there's a 1 here. So that just basically propagates all the way to here. And then we have a borrow from this 1, which means the most significant bit is going to be a 0. So that's why 1 followed by 7 zeros minus 1 is going to be 0 followed by 7 ones. Okay? But this time I want to answer the question of the overflow flag. Should the overflow flag be a 1 or should it be a 0? That means we only have to focus on this column here. Okay? There's an implicit 0 here. The first number is a negative number. I'm subtracting a non-negative number from a negative number, and we end up with a non-negative number. Does the sign of the result make any sense? It does not make any sense. That means the overflow flag should be a 1. Okay? So we have all of these things. We work out everything, and then then we can run the program and see if this can be confirmed. Are we kind of doing okay so far with this example? Okay. So let's go ahead and do this. A as G stabs dash O sub1.O sub1.S LD sub1.O. Put a breakpoint on line 6. Run the program. Now we are on line 6, single step. And then we say, okay, show me what is AL. Well, it shows AL as negative 128. Not 128. What is going on here? As an 8-bit number, if you want to look at an 8-bit number as a signed number, 80 in hexadecimal represents the value of negative 128. On the other hand, if you want to look at it as an unsigned number, then it is just 128. It's the same bit pattern. So depending on how you want to interpret it, it can represent negative 128 when interpreted signed, or it can represent 128 when interpreted unsigned. Is that okay? All right. So now we single step, we subtract 1 from this particular bit pattern. And the first thing we want to do is to say, okay, show me what is AL. And we want to show that in binary. It is 7 ones. If we want to show that in hexadecimal, it is 7F. So that part is confirmed. But we also want to know what are the flags. Okay, so IR or info register E flags will display the flags. And we can see that the only flag that is displayed here is OF. The other 2 flags we don't really care. Okay, so whether they are set or not does not really matter. But we can definitely see that O flag or the overflow flag is set. But the other 3 flags are cleared. So everything does work out the way they're supposed to. Is that okay so far? It's all good? Okay. But subtraction is useful, but sometimes we don't want to store the result of the subtraction. So in order to understand why we want to do subtraction, but without storing the results, think back in C and C++. Okay? What is the most basic and useful construct that gives you a Boolean value in C and C++? When you write a program, and you are using either a loop or a conditional statement or something like that, okay? What do you put in the condition part? Comparisons, right? Okay, so you have comparison operations. So let's go back and just kind of take a quick look at the comparison operators that we know of and see why it is related to subtraction. All right, so here's mousepad, and all I'm going to do is to show you stuff that you already know. In C and C++, we can say greater than or equal to, less than or equal to, not equal to, and equal to. Right? These are the 6 basic comparison operators. The first thing is I would argue and say I don't really need 6 comparison operators. I can shrink everything down to 1. If I can determine whether something is less than something else, the other 5 can be represented by just less than, and then a whole bunch of logical operators. Is that making any sense? Let's see how to make that work. Okay. So we can say How do we represent x is greater than y using only less than? Change the order, right? Okay. How do we represent x is greater than or equal to y using only less than? Right? If x is greater than or equal to y, it has to be the case that x is not less than y. Okay? Less than does not need any mentioning. So x is less than or equal to y is the same thing, but this time we say y is not less than x. Right? What about not equal to? How do we use just less than and some logical operators to represent not equal to? X does not equal to y is? Yep, that's exactly it. All right. And then the last one is x does equal to y. What do we do about this one? That's right. Okay, very good. So not y is less than x and not x is less than y. Oh, okay. So that means if I can determine whether something is less than, I can answer all of these questions. I can do all the other comparisons just by understanding, just by knowing how to compare and confirm just less than. Is that making any sense? Okay. All right. So if that is the case, how do we determine that? Okay. So the question is, how do we know whether x is less than y? But only using constructs and concepts that we have talked about in this class. What is the one thing that is going to do this? Subtraction. Okay, so we can do subtraction. Tell me again, how is subtraction going to do this? Okay. Okay, so it depends on one thing now, okay, because in the subtraction, okay, first of all, let me ask this. Does it depend on whether the numbers are signed or not when we work with subtraction? Think back in your subtractor homework assignment, okay? Does it work for signed numbers? Does it work for unsigned numbers? It works for both, okay? Subtraction, the subtraction mechanism that we talked about does not really care about the sign of whether the number is signed or not. Okay. Is that okay or not? Is that okay? Well, let's do one example just to confirm that we know that part. Okay. So what we'll do is we'll take a look at FF as an 8-bit number minus 0, 1. Okay. So when I use hexadecimal, it is basically implying I only care about the bits, the zeros and ones, but I don't really care about the signed versus the unsigned interpretation. Okay? So if you do something like this, you already know the end result is going to be FE or 1111 1110. Okay? Does that part depend on signed versus unsigned? No, it only depends on how the subtractor is defined. And I think most of you still remember how a half subtractor works and how we combine two half subtractors into a full subtractor, and then we can have multiple full subtractors connected to each other. Okay? Okay, now let's take a look at the values represented by these bit patterns. The first one is going to be the signed interpretation. Using FF as an 8-bit number in signed interpretation, what value is it representing? -1, okay. So we have -1 here, and what about 0, 1 in hexadecimal? What value is it representing? As an 8-bit signed number. Well, that's an easy one. 1 is always 1. Okay, so we have 1 minus -1 minus 1, and what about FE? What is it representing as a signed value? -2. Okay. Oh wait, but TAC, how do I know that FE as a base 16 number is representing the value of -2. How do we know that? We know it's negative because the sign bit is a 1, but how do we know how negative it is or the magnitude of being negative? 2's complement, very good. I heard 2's complement. So if you know, FE is a negative number and you want to find out what is the absolute value, we just have to apply 2's complement to it. So 2's complement of FE, okay, I'll first convert it into binary first. So we have 1, 1, 1, 1, 1, 1, 1, 0 in base 2. And what is 2's complement? What do we do with 2's complement? It's 1's complement plus 1, right? 1, 1, 1, 1, 1, 1, 1, 0 in base 2 plus 1. And what is 1's complement? What does it do? It's a bitwise negation, okay? So it negates all the bits, okay? So that means all the 1s turn into zeros, all the zeros turn into 1s. So we have 0, 0, 0, 0, 0, 0, 0, 1 in base 2 plus 1. And what is that? In base 2, which is representing the value of 2. So if the 2's complement of 1, 1, 1, 1, 1, 1, 1, 0 is representing the value of 2, what do you think 1, 1, 1, 1, 1, 1, 1, 0 itself is representing? Negative 2. Okay, so it works out. Okay, if it works out in the signed way, what about the unsigned way of looking at this number? I'm just going to copy and paste it here so we don't confuse it. So what is the if I interpret 1, 1, 1, 1, 1, 1, 1, 1 unsigned, what is the value that it is representing? 255, okay. 1 is always just 1, right? That's the easy one. What about FE? What is it representing? 254, and it works out too. So this is showing you that subtraction, the bitwise subtraction mechanism that we have talked about, which is what is giving you this particular result, it is sign independent. Okay, the values can be signed, can be unsigned. It doesn't matter. It still works. But the biggest question is, but how can we determine the ordering of numbers? Whether the second number is less than the first number, whether the first number is less than the second number. That's the question. Okay. So in the subtraction, we have one value, V1. We have a second value, which is V2. In the comparison, do we care about the actual difference, the end result of the subtraction? No, we don't really care. So we'll just say question mark, question mark. What do we care about are the flags, okay? All right. So in the case of unsigned, V1 is less than V2. Okay, I know this looks really odd because I use the angle brackets and there's also a less than subtraction operator here. How do we know whether V1 is less than V2 when these numbers, when I am representing unsigned numbers? Which flag do I look at? No. If it's unsigned, I don't care about the sign flag. But which flag is going to be useful? The borrow flag, which is also known as the carry flag. Yep. Okay. All right. So the confirmation that V1 is less than V2 is the carry flag being a 1. Now I use IFF. It is not a typo. It stands for what? If and only if. Okay. Is that important? Why is it important? Because if it is just an if, it doesn't say exactly. It doesn't say anything about the else. Okay, But if it's if and only if, that means one implies the other and the other way around as well. Okay, so that's a very important thing is to use IFF, if and only if. Which also brings me to something, a little side trip here, okay? Because in C and C++ and all programming language known to man and women and other programmers, because these days you have to be, careful, politically correct, and it takes a lot long. It takes more to talk about that, So I would just say any developer. So to any developer, we are used to something like this, right? If x is less than y, then we specify that we want to do the following. We say printf less than. Okay, so let's just say that we are looking at this chunk of code, and everybody in this class should know what this means, right? I mean, some of you use C out, in your C++ class, but it's the same thing, okay? It just prints a little message and say less than. That's all it says. Okay, so we know that if we see the message less than, x is less than y is for certain. What about x is not less than y? What is this code supposed to do? Now, that is a trick question because it depends on, are we talking about in the context of C and C++, or are we talking about the context of the word if in a logic sense? Okay? So I'll answer those two questions separately. The first question is, in the context of C and C++, if x is less than y is not true, it will simply go to the else statement, which is empty in this case, because if it's not specified, it is just empty. So it's not going to print anything. Is that okay? But what about in the logic sense? In the logic sense, if we say if x is less than y, print f less than, does it say anything about what to do when x is less than y is not true? It doesn't say anything about that. Okay, which means if this is if a logician, okay, somebody who studies logic, is to take a look at this code here, the logician would say, well, but you don't say anything about what happens when x is less than y is not true, which means it can still print less than in that case.
If the statement is false, the way that you have it notated, it wouldn't go into that box.
If that is my intention, if the intention is if the condition is false, do not print f, I should have said if and only if. This is a fundamental flaw of all programming languages. They picked the wrong word. Instead of using IFF, if and only if, for conditional statements, they all use the wrong word, which is just if. No, the else is fine. If you want to specify else, that's okay. It's not a problem. But in many cases, we only have something to do if the condition is true. I should say if and only if the condition is true, right? Then you don't have an else statement. If you don't specify an else statement, it is if a logician is to take a look at this code using only the word if, the logician can argue and say if x is not less than y, we may or we may not print less than. It's just that if x is in fact less than y, then we for sure will have to say less than. Yep, go ahead. Implies, exactly. X is less than y implies we should print less than.
No, the second f is implied. It's actually there, you just don't see it. The second f.
You mean the if and only if part? But you cannot say it is implied because if is not the same as if and only if. I'm nitpicking here, okay? I'm nitpicking, all the people who wrote or invent, programming languages, but I'm basically saying they all picked the wrong word. They should have used if and only if and not just if.
I'm pretty sure they all meant to do a double F in there for the efficiency.
that one extra keystroke, right? Yep. Well, but as a mathematician, this is an important thing. I mean, it really makes a big difference, okay? All right, so for unsigned numbers, we know how to deal with it. What about signed numbers? In other words, if I have two values, they are represented as signed numbers. If V1 is in fact less than V2, how do we know that is the case? We talked about this also, but it was a little bit of time ago, so can anyone remember which flag? The L flag, very good, okay? So the L flag being a 1 is basically saying L1 is less than L2, V1 is less than V2 in a signed interpretation. But there is no such thing as the L flag. What is the L flag defined to be? Yep, the L flag is the sign flag, exclusive or with the overflow flag. That's correct. Okay. Oh, well, that means, subtraction is in fact useful in comparison. It can tell me the ordering of values, whether I want it to be signed, which means I have to look at the sign flag and also the overflow flag, or unsigned, which means I have to take a look at the carry flag. But when you compare, okay, so when you have a line of code in C and C++, like the one we have here, oh, I just erased it. Okay, never mind. Okay, so I'll just put it here again. If x is less than y, and since I'm here, and just talked about it, let's use if and only if. And for those of you who say, but there's no such thing in C and C++, fine. Okay, now there is. Okay, all right. So when we actually specify this code in C and C++, okay, after the comparison, did anything happen to x or y as variables? No. The subtraction might have happened, but did I store the result of the subtraction? Nope. Okay, well, that's easy to understand in C and C++. But it's a little bit harder when we have a subtraction instruction that always stores the result into the second operand. There's an easy way to get around it, right? Okay, because you can always just copy the second operand into a register that is not being used and then perform the subtraction. So now, even though it does change the register, it's not the actual thing that you care about. You can use a temporary place you can use a register as a temporary storage area, so the actual result is tossed away.
Is this the only way to overwrite the second operand? There is no other subtraction mechanism?
There's another subtraction mechanism. It's called compare. Okay, so what we'll do is we'll copy subtract 1 to compare 1. Okay, and the only difference, if you want to compare instead of subtract, in other words, in this case, if I just want to compare 80 as a bits to 1 as a bit, but I don't want to really store anything into AL, all I have to do is to change SUB, which is subtract, to CMP, which is compare. So the compare instruction is exactly the same thing as a subtract instruction, except for one thing. What is the only difference? It doesn't store the result. All it does is to actually carry on the subtraction mechanism, but it doesn't store the difference. But it does set the flags the same way, exactly the same way. Okay? So let's go ahead and just run this program, as an example, just to be sure. So G stabs-o, cmp1.o, cmp1.s, link to cmp1, cmp1.o, gdb, cmp1, put a breakpoint on line 6, okay, so run the program, single step, print AL, it is -128, which is fine, and then we run line 7. So after we run line 7, the first thing we want to do is to say, did anything in AL got changed? Nope, AL is still the same as before. Then the second question is, did it change the flags the way it's supposed to? Because it should change the flags the same way as the previous program. I did not change the constants. All I did was to change the instruction from subtract to compare, right? So if I look at IR, which is info register E flags, we confirm that only the overflow flag is set. All the other 3 flags are cleared. Is that okay so far? Does this kind of help illustrate, the difference between a compare instruction and a subtract instruction? Okay, very good. All right. Are there any questions at this point? So we know how to compare. Yep, go ahead. Can you ask the question again?
So the E flags are a different register?
E flags is a register, but that register is normally not accessible as a general purpose register. But the debugger has a particular command to access it. Okay, any other questions? Okay, if there are no other questions, we'll go ahead and take a look at the C code again. Let's just look at this code here. We know how to compare now, okay? But what is the result of the compare? The general description of the comparison instruction is what is the end result? What does it do? Okay, well, you're right. Okay, so we have the 4 flags that we have talked about, right? The Z flag, the O flag, the S flag, and the C flag, right? And the subtraction instruction will affect those flags depending on what is being subtracted from what. Is that okay so far? Well, a whole lot of good that's going to do us, because we need to do something in addition to that. Because when you look at this C code, okay, what does it do? If x is less than y, we want to perform the operation. But if x is less than y is false, what do we want to do? We want to branch around and skip that portion, right? In other words, we have to somehow be able to utilize the result of the comparison. And at this point, there's no instruction to do that, because we haven't talked about those instructions. Okay? Let's talk about the instruction, or the family of instruction that will be helpful for that. And we'll take a look at the, that's the wrong part. I'm going to go to assembly language programming. These are the jump instructions. So we want to go to jump instructions here. And we have a whole bunch of jump instructions. The first one is easy. It's called the unconditional jump instruction, or otherwise known as quote-unquote go to. Okay? So I'll give you one example of the go to instruction. And this one can be quite easy. The jump instruction is JMP and not JUMP. And you basically specify the location where the next instruction is supposed to be. Yep. No, I did not bring my row sheet today, so we're good today. Okay. Okay, so what do you think this program is going to do? Okay, so once again, let me describe what a jump instruction is going to do. The jump instruction is unconditionally going to continue execution where the operand is specifying. So what do you think this program is going to do? It's an infinite loop, right? Because it continues execution at label underscore start. But what instruction is at underscore start? The jump instruction itself, right? So when you run this program, it's not going to be a whole lot of fun. You cannot even really quite see the infinite loop, because it's just going to be the same instruction over and over again. It will make you think that the debugger is not working. So to make this program a little bit more obvious, we will insert a no op here. So you can see it will alternate between the no op and the jump instruction. Is that okay? All right, so let's go ahead and just do this. I mean, this is a pretty easy one to see. Gstabs-o, go to.o, go to, whoops, there's an additional minus there. And link it. List the program, put a breakpoint on line 3, and we'll run the program, single step, single step, single step, single step, single step, and so on. Okay? Not very exciting, is it? Okay? Because it's just an infinite loop. I'm looking at the time, I'm looking at the architecture. Let me show you the architecture first, okay? The toy architecture that we have been talking about, because I want you guys to think about, but how do we implement this in the toy architecture, okay? So let's go to the home folder here, run logicsim, and I have to remember where I put my file. So let's see if it is here. Text processor, that's the old one. Nope. Okay, let's go to, I'm going to download the architecture from the homework assignment here. This time I will save it into my user folder, so this way I don't have to re-download it. Okay. So file open to parent folder, version 2. There we go. Okay. So now we have the toy architecture. And if you look at the toy architecture, I can shrink this part here. It's not that useful. Okay, so if I want to implement the jump instruction, which register do you think it is going to be useful in this case? Which register controls where the program is going to execute? No. Program counter. Okay, the PC or the program counter is the register that is responsible to control where's the next instruction. Okay, so if I want to implement an unconditional branch instruction, what do you think is going to happen? Assuming the PC, the program counter, is pointing to the instruction being executed, which is going to be the branch instruction. So what do you think a branch instruction would look like? Or what are we actually doing to the PC, to the program counter? Okay, let's take a look at the program counter. The normal way to use the program counter is simply to increment it so it points to the next location, because normally the flow of a program is just executing consecutive instruction in a sequential way. Does that make any sense? So that is why we have the increment mechanism, which is the adder, and the pathway to go back to a mux to go back to PC, because that's the auto increment method to make sure the PC goes on to the next location, the next location, and the next location, and so on. And if you look at all the registers that we have, the PC or the program counter is the only register that has an auto increment mechanism. The address register does not have that. The other registers in the register bank, they do not have that either. The program counter is the only one that has the auto increment capability. But you can also see the auto increment ability is not the only thing, because when you look at the pathway going into the mux here, this is one way, which is the usual way, is to increment to the next location. But there's the other pathway as well. What is the other pathway connected to? Which is this link here. It connects to RAM, but to be more specific, which port of RAM do you think is connected to? I know it's not shown here, but I think some of you remember. It's the data bus, the data port. Okay, so that means there is a way to go to the data bus and read from the data bus and use whatever is in the data bus to program or change the program counter. Okay, what does that really do? If you change the program counter, what is that effectively doing? It's a jump, because the next instruction you execute will no longer be the one following the program counter. Well, that's an option, but you can go anywhere else you want. Is that making any sense? Okay, so I just want to show you this because I want to show you how this is actually going to be implemented at a low level inside a processor. A branch instruction is simply saying overwrite the program counter with this value. Okay, and we have 2 minutes left. Okay, with the 2 minutes remaining, I will show you the more interesting branch instructions. These are called the conditional branch instructions. They may look like much, but they're very, very useful. Because what it means is, okay, let me just kind of scroll down here. Okay, we'll just focus on one. Okay, we'll focus on JC, which is saying branch or jump if and only if the carry flag is set. What if the carry flag is not set? It's not going to branch, which means it keep going. Exactly. This is the only way we can have branching in assembly language programming. You look at the flag, pick one, and you say, if this flag is either 1, or you can use JNC if you want the reverse of that. But you can look at a single flag and say, based on the status or based on the value of this one flag, okay, I can decide whether to branch to the location specified by the instruction, or I would just continue with whatever instruction is next to it. That's the only branching or decision-making mechanism in assembly language programming. Yep?
So in your if and only if x less than y, print less than, when you say that it'll continue, you're already saying that it'll go into the body?
Yes. Well, it will go to whatever is next to it.
So, but if x is not less than y, will it
Okay, so JC is usually also has a label next to it, and the way it works is if the carry flag is set, then it will go to whatever that label is specifying. On the other hand, if the carry flag is cleared, it will just continue with whatever instruction is next to it, or is following it. Okay, so we'll take a look at this again on Thursday, but I do want you guys to read this part here. Okay, the add instruction, it's kind of like a move instruction, except it adds the first one to the second one. The subtract instruction subtracts. Okay, the compare instruction is like subtract, but it doesn't store the result. So those instructions are kind of like a move instruction. It's not really that special. These instructions are very special because they can change the way your program flows. Where is my next instruction? Yep.
Can you tell it like what line to jump to? So you go like JC at 20?
You can specify a label.
Oh, okay.
So you can define labels where you want it to branch to and then specify the label. So we'll talk about this. We'll continue this on Thursday.